Torch this computer. All right. Okay, everybody. Welcome back to round 2 battery knowledge transfer for NFR 23. As I mentioned in the channel, but in case you haven't noticed, as always, I am recording these. The goal is that you come in person, which I appreciate all of you coming. To all of you on Zoom, fuck you. I know, but that's the people who watch the recording and all that stuff, and I'll be like, hi, and they'll know I'm talking to them. Anyway, yeah. So hello to everyone who came in person. Hello to everyone on the recording. Yeah. So for anyone that didn't realize it, like I said, Dennis took notes at the end, like throughout last meeting, and he graciously put all of those on the end of the slide deck because I know there was quite a bit that I winged at the end of the last presentation. Anyway, we'll now be moving forward with this next slide deck that we'll be mainly focusing on the segments today. So from a high level, I've broken this down into 3 major components. The segments are going to have the actual parts of the segment itself. And then we're going to be talking about the configuration and orientation of cells within a segment. And then finally, we're going to talk about the larger configuration of segments within the whole. And so that's going to slowly work our way out to what are the parts that we need to consider, and then how do we arrange the cells within it, and then finally how do we arrange the whole pattern of that. And then I'll sort of show off an example design that, at least from my interpretation, is potentially fixes a lot of the concerns and problems that we've seen this year, but is by no means a perfect or finalized design in any way. Okay, so let's start off with the components. So as you see, I used to draw shit on the board, but it didn't come out super well. So now I've made an awesome, cute little graphic in here. Look at that. Wow, it's so cute. What's up? Yeah. And so that's the thing is, yeah, now we have this cute little graphic. And the basic idea is that our battery segments are broken up to all these different parts. First, we have the E-box on the outside. The E-box, the main goal is that it will to sort of give us this container, this enclosure that sort of holds the rest of our battery. If this was just raw battery cells, I couldn't really safely pick this up because, it would be all with batteries and I would chuck. So that's why we have the E-boxes, because number one, by rules, we need to have an electrically insulating, flame-proof barrier between segments. And number two, it makes it really nice and easy to work with safely, and only if I pull it out of the package. Oh, sorry, pull it out of the end. So yes, these current E-boxes are made out of polycarbonate. The final E-boxes are going to be made out of CPVC, which is high temperature PVC. The reasoning is because it is the only material that we could find in the thickness that we wanted on McMaster that also had the UL94-B0 flame rating that we needed. People can use the reason we like to keep them in these so far is because they're clear, and so it's very aesthetic. CPVC is opaque gray, which is very boring. But yeah, the idea is that we're gonna be using these, and then we already have the material in. So once we get all of those cut and ready, then for the actual competition, we'll swap them over into the sad gray boxes. So
why is it called E-box?
So we have now adopted the very generic term on the team of any box that stores electrical stuff, we are calling an E-box. Wow. And so that's why if you look through our other things on the car, you'll be like, oh, the box that has all the stuff in the front, it's called the dash box or the E-box. And so now we've always called just our box that we put electrical shit in, E-boxes. That's why we call it that. I don't know if that's a standard term. You could call it something different. That's just sort of the name we came up with. So the rules doesn't say you need to have a box. The rule says you need to have electrical insulation on the sides that face the segments, on the sides that face the sides that face another segment, sides that face the exterior, and the upper face. And the idea is that if you had let's say 2 segments, if you were to drop a tool in, you couldn't accidentally electrically short the container to the actual segment or one segment to another segment. And so, if you think about it, that means that at least with our configuration, we need 5 of these 6 sides. So we might as well just make a box rather than having 5 floating sides that are all electrically insulated. Yeah. So that's the E-box that goes around the outside.
So you just hold and E-box?
Yep. So right now I don't have a lid on this one, so because like it's easily thought of in. But yeah, normally there'd be a lid on the top if we have it on all six sides and it'd be held in. And then the idea is that yeah, if you wanted to like do any actual service or maintenance on the pack, you would pop the lid off, you'd have to unbolt a few things from the top, and then we'd be able to do is you actually be able to slot the whole thing out and you get what we suppose like. That's how you would service something with the battery management system, or if say one of the connections in there broke, then you service those. So yeah, obviously I'm not going to pop this one out. Number one, because if we take them out, we have to wear gloves because, like, once you go above 60 volts, you have risk of electric shock. Yeah, once you go above 60 volts, you're at risk of electrical shock or damage to yourself. And this battery pack goes up to 84 volts. So for like the safety reasons, we're not supposed to do that. And so yeah, we just have the practice on the team of if you're ever actually going to be taking this, and here I can use it with my hands, but as soon as I'm taking it out, I can grab it for. Mainly because A, from a shock perspective, I don't want to be electrocuted. And then B, from like a protecting the segment perspective, I have oils and things on my hands that if they get on there, they can make it easier for the segments to arc, and they can also corrode the segment. For the box, so luckily at most forms of plastic, there are special, I don't want to say epoxies, but there are special adhesives. But what you can do is they actually like melt the base material and can adhere it more effectively. So like, with something like super glue or epoxy, you're basically just like putting glue in between. You're not really doing anything. But for both polycarbonate and CPVC, you can buy a special goop that will actually like melt the material and make it one piece of plastic. And so that's the plan. Is that we'll basically have someone go through and make a seam on both sides and then scoop it out to make sure that we don't have any fillets or anything. Real compelling. Real compelling. But yeah, so that's what's going on. That's the whole situation there with e-boxes. And then, obviously also I'm going to go into detail about each of these components on further slides. But yeah, so that's a high level structure. E-box sits on the outside. That sort of protects the battery from the rest of the world and the rest of the world from the battery. Then we go into the actual cell holders, which apparently companies sometimes also call a cell matrix. That's obviously this is a cross-section view, so it's kind of hard to identify how it's a big structure. Like sort of showing it off here is way easier to see. The cell holder is white thing. So this is like all that we've done is it's 3D printed out of a highly glass filled plastic. This in particular is I think 40% glass filled Pt.2. And so they use like a special type of 3D printing called MJF or multi-jet fusion to be able to print the shape, and then a company that sponsored us into this. In the future, we're going to be moving to a different type of 3D printing. Rather than MJF or multi-jet fusion, we're going to probably be moving to FDM, which is your standard 3D printer head, prints a thing and moves a bit. That's probably the structure we're going to move forward in the future with, because we can do that in-house. It's way cheaper. We have a lot more flexibility, and we can actually print weirder shapes because we have a printer that can print infinitely long items. So it gives us more flexibility with the cell holder shapes. But yeah, so obviously, if you think about this, if you were looking at like a cross section of these cell holders, you would end up seeing these little like T shapes on either side, and that's really what's going on. Is that you have these T shapes, these are the sort of cell holders, so it's all these white parts, and then as you can see, you actually have these standoffs that stick out from parts of them. You'll see it on either side, and you can actually, when you look at it on here, you can see it as like the swivelly parts that stick out. You can clearly see that like the bonds are all hidden inside there, and then the standoffs actually like stick out above. So that way, as I apply a force here, I'm not going to actually press directly with the plus bars or press directly on the bonds. I'm instead just applying force to the standoffs and then into the cell. The big thing also that I sort of want to call out in this upper region is the fact that we have these tall boys that sort of stick out. That's sort of what you can see in here. We have this upper region of the cell holder where it sort of allows us to protect the BMS board. Because the idea is that this battery pack, as a reminder, has to be able to take 40 Gs of acceleration in the lateral direction and 20 Gs vertically up and down. And so that means that if we have to prove through FEA that we can take a 20 G load upwards, you basically imagine I took the pack, flip it upside down, and dropped it. I obviously don't want this PCB, this little piece of fiberglass, to take all of that force and all that load. So instead, we make the cell holder stick up extra high. Instead instead we make the cell holder stick out, so that way it can take those forces and take those loads from it. Yeah, so obviously that's sort of what we're depicting here. But as you can see, we actually have this, you might even see it in here. You can see we have this nice little lip. You can see it also in the visualization. We have this nice little lip that the BMS board can actually sit on top of. And the idea is that, and so the BMS board can sit on top of. So that way it makes sure it's not just like sitting directly on the cell, because that would be bad. And instead we can support it, but we can also keep it very close to the cells and we can actually hold it. So yeah, that's the big thing with the actual cell holders. Now moving over onto the bus bars, this is something we once again talked about last time. These are the electrical connections sort of between the actual, like these pieces of metal that are between the actual cells, and it allows us to sort of make sure that we have all of our cells in parallel fully connected to each other. So if you look at the battery pack, you can see the actual strips of metal in there, and those are those silver strips. Those are the bus bars. In particular, our bus bars are nickel-plated copper, but you could also do something like an aluminum bus foam, or if you wanted to be really inefficient, you can make like steel bus bars. No reason to do that. Yeah, so those are just the pieces of metal, sort of make sure that if I connect these cells to these cells, that their voltages are all actually tied together in parallel. Cool. And then, as we sort of talked about last time, again, the bonds are these connections between the surface of the cell and the bus bar, and those give us overcurrent protection. And number one, it's actually one of the only ways that you can transfer a high amount of current from a battery cell to another piece of metal, unless you're like mechanically clamping it on and that has other problems. So we have this dual great functionality of A, it's a great way to be able to actually get current from the surface of the cell to another piece of metal, and then B, there's this overcurrent. Where it's like if you draw too much current from it, the idea is that the bond will fuse and melt before the battery can be which isn't super accurate, but whatever. Obviously, we have the cells. That's the battery cell itself. I don't need to explain what a battery cell is. And then the last two things that we have in here, obviously, is the BMS sensing connections or the battery management system sensing connections. Like I talked about last time, the battery management system has to actually detect the voltages and temperatures of all the cells in the battery pack, either directly or indirectly. For voltages, it detects all of them directly. And for temperatures, it measures the temperature near every cell, and we can use that to approximate what the whole pack's temperature is. And the reason that I sort of am calling this out is this ends up being a major concern and complexity for the design of the cell holders and a lot of actual mounting and packaging. Is that you see we have our battery management system board here up at the top, but then the way that a lot of teams do it and the way that we were originally planning on doing it is you would have a wire that would run from that board. You know, there'd be a connector, but it would run up and around and then would go down and it would touch each of these bus bars. And the idea is that then by touching this, I can tell you what voltage this cell is at relative to the next one. And so I can sort of compare all the voltages and we can always monitor those, track those to check to see if something's going wrong. Similarly, you would have another set of wiring that comes down and does your temperature sensing. So you'd have, say, a temperature sensor like a wire that would come down and stick on here, and it would measure the temperature of a cell in the battery. Cool. So yeah, obviously this is high level. We'll go into more details for everything individually. The actual BMS board itself is pretty clear. That's obviously not within the scope of the actual battery pack project. There's a separate project that handles all the BMS PCBs. Those are very complex and definitely their own thing. You wouldn't be expected to design those, but it's something that you would have to interface with a lot because obviously the battery pack is useless without the battery management system, and the battery management system is useless without the battery pack. One thing that we did this past year is we kind of designed the pack and designed some of the battery management stuff and then didn't really finalize all the details. And then we now had a few issues where we had sensing and connections that we had things that could work, but they had lots of points of failure and it was kind of sketchy. And now we sort of had to do a lot of weird engineering to overcome the fact that our designs weren't fully and completely designed cohesively from the beginning. And then finally, we have our maintenance plugs. So just like you have these bonds that go to your bus bars and it sort of keeps jumping through the different cells in order, you have a maintenance plug. Because like we mentioned last time, your battery pack has to be broken up into chunks that we call segments. And there's a name for the plug that connects one segment to another segment. That name is a maintenance plug. And the idea is that the maintenance plug is a toolless plug that you with your hand could go in, grab, and use to disconnect the battery pack. You have to actually be able to use maintenance plug to disconnect both poles of a battery separately. So you can't just have like a fucking cable that sticks out and plugs into the next one and then you have to have two fully separate plugs that you can completely unplug it and take it out. So cool. And yeah, the big idea though, I emphasize with the maintenance plugs, it's not anything special. It's really just like a connector that's able to handle really high currents for our battery. It doesn't actually even do any data transmission. That's so yeah, this is our high level of the segment components, and now we're going to sort of dive into the particular requirements, the designs that we have this year, and then a lot of the recommendations that we're going to give for next year's designs. Some of these obviously are going to be more electrically leaning. Some of these things are going to be more mechanically leaning. But the main thing I want to emphasize, the reason that I'm doing this in one sitting is that all of the electrical considerations fuck with the mechanical stuff, and all the mechanical considerations fuck with the electrical stuff. You all have to work together to make it work well. Otherwise, you'll have a repeat of this year where you do twice as much work because the factory didn't integrate it properly. They could, but they're not required to, so we don't. Yeah, so Joshua asked a good question about interlocks. An interlock, for anyone who doesn't know, is how normally you have like a connector where it'll say conduct current or whatever through a plug. You can actually get special types of plugs that will have another really small connection that goes through it that lets you detect if you plugged it in properly. And the idea is that you can then have like safety circuitry that goes through the small connection, and then major power or major voltage that will go through the large connection. And then you can have your circuitry detect that you plugged it in properly before it actually turns it on and starts doing stuff. So per se, you hadn't plugged it in properly. The idea is your safety circuitry will be like, well, this plug isn't plugged in correctly. Don't even try to turn anything on. This is not plugged in. There are connections in the battery pack that do need to have interlocks, specifically like the main connector for the battery. But the maintenance plugs do not need to have interlocks. There are maintenance plugs you can buy though that do have interlocks. We just don't do them.
Not having interlocks isn't a safety issue, but I'm just thinking like if we accidentally don't plug one of them in, then the BMS will be happy to turn on the car and it'll read all the voltages correctly and everything will look fine and not get that.
Yeah, and that's why that was one thing that may potentially be a good avenue in the future, is that if this is something we regularly notice as a problem, it could be potentially moving to having interlocks in all of your connections in the battery pack, or some similar way of identifying that they're plugged in properly. Might be a good thing to add. 30 minutes in on the first slide. 45 more slides. Okay, so yeah, if we don't finish today, it's fine. We'll continue next time. Yeah, so starting with e-box. E-box is, I would say, the simplest thing. It has the fewest areas of improvement, and it has really the fewest complexities. Like I said, the rules and requirements for it are pretty simple. You need to have some holes so that you can get cooling in there somehow, whether that's liquid cooling in the form of tubing or cold plate, or that's air cooling in the form of just holes. Obviously, this year's design, since we did air cooling, we just have a bunch of holes on the side that air can blow through. If you actually look on the segment, wow, holes.
They're lined up. They are like
optimized,
such that there isn't just air going into like a wall.
I didn't epoxy it.
This one
I know. Anyway, yeah, everything has to be holes. You can't have slots. Just sad.
That's in the container, though.
That's in the container. Yeah.
So the e-box could have
Yes.
slots, but we want it to line up. The whole pattern on the e-box lines up with the whole pattern.
For the Zoom recording, Louis was explaining how in the container we're not allowed to have slots. We're only allowed to have holes.
Container, meaning
So the actual the larger accumulator container by rules isn't allowed to have. What's up?
Sorry. What was that? What did you say to me? Fucking then kill us all. We're just gonna die.
Anyway, yeah. So that's one of the big things with the accumulator.
Jeez.
Have you finished? Oh yeah, we ran the Sims for that.
For that one.
Yeah.
Where did you?
Yeah. Anyway, but yeah, so that is one of the cool things to point out, is that your cooling methodology interface and how air flows through the pack is definitely an element of consideration when you're designing stuff like these airflow holes. But generally the box itself is a pretty simple thing to design. Like I said, it needs to have holes so that way the connectors can stick throughout the top. Same thing, it needs to be electrically insulating. Obviously, basically any form of plastic will have way more electrical insulation than you need. Technically, in the electrical systems form we need to submit, they do ask you to calculate what your voltage rating is, but any amount of plastic is going to always have a voltage rating of many hundreds of volts per millimeter. And yeah, and anything that's going to be UL 94 V0 flame rates, anything that meets our flammability rating, other than fucking steel, Anything that meets that rating is usually already, you know, in the range of like 1/8 an inch to 1/4 of an inch thick. And so at that point, your voltage rating is already into like hundreds of thousands of volts usually. Like I think this has a voltage, like this with the polycarbonate has a voltage breakdown of like 50,000 volts or something. So, you know, obviously we don't get anywhere near that.
Meaning it's 50,000.
So yeah, so like I could put like 40,000 volts across this. I don't do that. Yeah. Yeah. And so the last thing also is that like functionally, like I sort of mentioned earlier, one of the big reasons that we have these e-boxes is so we can actually sort of safely work with them and move with them. So, you know, you could theoretically cover your segment in tape. I think there's a rule specifically that says don't do that. But like, you know, in theory, you could meet all of your like electrical insulation requirements by just covering in all like flame rated cap down tape. But the problem is obviously you wouldn't be able to really safely pick it up and move it around because it would still be pretty squishy. And so that's why we made a rigid box. And it actually makes it really great and really easy to work with. And I do recommend that approach moving forward. Yes. Yep. Very big fan of it. Obviously, with our current designs, the big thing is that we manufactured some of them via water jetting and some of them via some of them through the router. Generally, it's more of the process of like, so, oh, and by the way, obviously this is made of 1/8 inch material. This is currently polycarbonate, but like I said, the actual one is going to be a CPVC or high temperature PVC. I'm gonna probably recommend that we maybe go more for the router in the future. The water jet works fine, but it's more of that we have limited access to the water jet and it's generally pretty slow. Whereas the router, we can basically get it whenever we want on the weekends, from what I can tell, based on how Aero uses it. And we can, and you know, it produces a similar level of quality to the water jet. So we'll probably end up pushing more for a router in the future. Yeah.
Into consideration in your like DXF designs, so you have to basically have on chain thermal port of these. So it's a little bit more overhead on the design, but it's pretty good.
Yep. And so that's the thing is that it's like it's all basically a trade-off of like if we have people with bandwidth to do water jetting, the water jetting's great. I know particularly it lined up poorly this year where the water jet was like fucking dying at the time. So we'd be able to do like one. And so the router ended up being sort of how we did like half of them this year and the water jet did like the other. But yeah, so don't care. And so that is fine. And so yeah, that's the thing going on there. Yeah. I can't.
You can't laser cut these.
Depending on the material.
Yes,
Like,
this
either
material.
both of these materials are
This one, I think it was from all behind the tower, but.
It's one of the bad guesses. Yes.
I think probably have been.
Yes. They all released the Danger Noodle. But yeah, anyway, so like I said, e-box is pretty simple, pretty straightforward, not really like this doesn't need to have like a big amount of time and energy to get to it. All right, let's talk about cell holders. Oh, what's up? Why is the segment itself a box? Oh, you're gonna love the set of slides in the setting.
Okay.
We'll get there in like an hour and a half. The answer is it doesn't have to be a box. If you want to make it not a box, it cannot be a box. And that might be a good design. Or it might be a bad design.
It requires more difficult thinking.
Yeah.
this was a good place to start.
Yeah. The TLDR for what those slides is going to cover is like there are so many configurations and options that you can totally do a bunch of gnarly, crazy shaped battery packs, and those may be significantly more optimal. And it's just if you have the engineering bandwidth and time to handle the additional thinking and complexity that comes along with weird shapes.
Do you have a screenshot of my lightsaber battery?
No, I do not. That's too far back. Anything else? Cool. All right, cell holders. The cell holders have been a monolithic monster of a project that Louis has been working on over the span of the last like year and a half. So I'm not going to go into every single detail of the cell holder. If you want specific details exactly about how the cell holders work, definitely just reach out to Louis, talk to him. He'll be able to tell you all of the pain and suffering with meshing and FBA and singularities and all the fuckery that comes along with it. Particularly because the fact that I think it's the first time we've ever done a load-bearing 3D printed part. That means we now have new interesting geometry and capabilities that normally we wouldn't have. Okay, but yeah, TLDR for the cell holders, but yeah, obviously they're super complicated. And the big part that you sort of saw back on the first slide is they kind of integrate everything. Like, the cells are held by the cell holders. The bonds are really just because of the fact that the cells are in that place. The bus bars are held by the cell holders. The BMS boards are held by the cell holders. The maintenance plug is held by the cell holders. Like fucking everything is held by the cell holders. Yeah, and like the E-box is really defined by the shape of the cell holder, more or less. Like everything is done by the cell holder. And so it ends up just being this really monolithically complex element of the project where everything else kind of has to be finalized and figured out before you can really finalize the cell holders, which is annoying because they also take quite a long time to run FBA on and be able to actually validate a design and manufacturing. So these are definitely the part that, like, if one thing is going to be the big blocker and the big bottleneck for battery pack design, it's going to be sinking time into the cell holders, just because everything else has to get done in collaboration with it for the cell holders to reasonably be finalized. Because like I said, this year we sort of finalized without figuring out all the problems, and then we had to do a whole bunch of mental gymnastics to figure out how to fit within the cell holders. So yeah, I already went over a lot of that stuff. The other big requirements that they have that I think are sort of implied, but I will highlight anyway, is, like I said, they need to be non-conductive. Because of the fact that it holds the battery cells directly, obviously the battery cells, they are just like exposed electrically conductive surfaces. And so if you took two pieces of like two cells and put them together into a battery pack, like into like a metal cell holder, you would short all the batteries together, and obviously that would explode. That'd be bad. So the big thing is obviously it needs to be non-conductive. So that's why we usually print them and manufacture them out of plastic of some sort. But the issue is that, like we talked about, there's all these great properties that come along with using bonding your battery cells. But because of the fact that we're bonding them, all those bonds are formed ultrasonically, which means your battery cell holders need to be very rigid. And so it means for your thing that holds everything also now has to be made of these way harder to print, more complex materials that have, glass contents or potentially a high carbon fiber content. And so like that's why, for example, this year all of our cell holders have been highly rigid, but they are like a glass filled plastic. So they're non-conductive, but they're still very rigid. They're linked on like one of the slides in the 50s. It's once we get to the bus bar stuff. There's a link in there. But yeah, and so then the big other thing is obviously, our battery pack is quite heavy. Our battery pack, just the cells alone, just weigh something shy of 40 kilograms. For all of you US people, that's about 100 pounds, which, probably weighs 100 pounds. Like that's like a significant amount of weight that you're holding with plastic. And it definitely is sort of like a significant amount of effort to go through, and like especially if you're looking at that visualization, you see that even though the cell holders look like there's a lot, in reality there isn't really much material in here as a honeycomb structure. It's actually pretty thin. And so even though we're dealing with one of nature's strongest structures fundamentally, getting the actual forces in FBA to all line up so that it can actually handle the 40G loads in all directions is quite a bit of work, quite a bit of effort. These print at such a high temperature that the battery, the batteries can't go above 60 Celsius, and these print closer in the range of 250 to 300 Celsius. So exactly. And so that's what I mean. It's like you're getting up to such high temperatures that it's like you could potentially see slight degradation in performance, but from like obviously we're getting nowhere near the temperature. So it's like, yes, you could potentially see a slight change, but we've expected that it's trivial compared to. Yeah, that's the whole thing. Yeah, 3D.
I have a question about have we done any analysis of like will the epoxy be able to hold plus bars on it?
No.
But also like they're not very
I mean, it's a big chunk of top.
You're a big.
They're very light though. Like it's not like no, we have not done any analysis, but like DP460, we'll see there's so much shit on our car that like
We don't crash that often.
I feel like it could be,
that often.
I feel like it could be worth just like doing a quick, what's the strength and how much force does it have?
I think there's potentially a good argument here that like I've already very strongly recommended and Hess has strongly recommended that we move to mechanical fasteners in the future. And the mechanical fasteners will definitely be more than strong enough to hold it. So it may just be a moot point because we can't we can't change it.
Right, but it's not trying to be
I guess. And sort of I guess that's what it's like but yeah, it would be good to know if we thought of this last year, but at this point it's probably not something that we'll be able to change.
right. I feel like probably using at least a rough analysis.
But how do you do that with the arbitrary? You're saying fix that problem by adding a proxy. I also think
Yeah, we'll wrap it back and we can make that a separate conversation. Anyway, okay, cool. And then yeah, obviously the main last two minor things that the cell holder has to do, as we sort of saw in the visualization, is the fact that obviously it has to be able to sort of allow for BMS sensing to actually connect to monitor the cells. So you could theoretically make a cell holder that fully restricts everything and makes it really well contained, and like all of your bonds and all of your bus bars are all really well isolated, so there's no risk of arcing or shock or like shorting between any two regions. But then how do you get the wires in there? How do you get the PCBs, the connections in there to actually monitor those voltages and monitor those temperatures? So you have to leave some amount of spacing, some amount of consideration for how you make electrical connections in there to monitor those properties. And then finally, the big thing is that obviously the cell holder, it's not just that it has to be able to withstand an impact, particularly it has to be able to, from like a larger perspective, meaningfully distribute force from the cells to the cell holder to the e-box and then finally to the container. So you sort of have to think about that whole pipeline. And that was actually something that, since we hadn't designed the container when we designed these segments, we actually ran into this big disjoint where actually we were effectively transferring forces from the cell holders to the boxes and then to the wall of the container, but then the container wasn't effectively transferring force to its mounts. And then we had to do this whole shakeup at the last second where we like redesigned all the container mounts. And so it's important to always think about how am I transferring all these forces to really go through the whole pipeline down to the frame. Yeah, there's more slides on cell holders. There's more slides on all of them. Yeah, so obviously our current design, like sort of highlighted, just the super high level stuff, we have two different types of plastics, different levels of glass filledness, depending on if you're looking at these guys, which are the 8 by 10 segments, or the long guy, which is the 4 by 20. So obviously they're using different types of 3D printing, like I said, MJF versus FDM. And then one of the big parts that I do want to highlight to sort of be like, don't just trust our magic numbers, is that we have quite a few magic numbers in our designs. A lot of them are driven by like, we picked a number and then ran some FEA and then refined it based on there. But it may be better to actually, from the beginning, do a more fundamental think through and design of saying, for example, the cell spacing. I believe the way that we got our like initial number for that was just like we found a design online and then we copied the spacing from that. And then we sort of, as we went through our FEA, we were like, okay, cool. We tweaked, we refined, we changed things. But fundamentally, we started based on like random. And rather than just going from an FEA driven approach, it may be better because, cell spacing affects the size of your pack quite significantly. That could potentially be better to say, okay, well, let's have this be a parameter that we're tuning, not just in FEA after the fact, but especially during the like initial pack sizing and pack layout.
Is there any regulations about how far apart they need to be? Or...
The cells?
Yeah.
So there are only regulations that say how far apart high voltage things have to be from low voltage things. From what I could find, I cannot find any rules that say what your spacing has to be between one high voltage thing and another high voltage thing. As long as yeah.
So you have to be careful about the part that
So basically their guidance is you should design it in accordance with good engineering disciplines. It's like, you're right. You shouldn't have like, a micron of space between your cells if they're going to arc, because yeah, eventually you're going to get them close enough that like, with like humid air and if salt accumulates on the surface and all those things, you can get a perfect storm where it's going to cause it to arc and then cause problems. Yeah. And so that's why we sort of, at least from the preliminary math that we did, the breakdown voltage of air is very, very, very high. And especially considering, even though these segments are at 84 volts, that's nowhere near the 600 volt peak of our battery pack. And so we do generally take a little bit more care when we're separating the full voltage of the battery. But yeah, from my understanding, there's no direct rules. It's more of just follow good engineering disciplines. And if there are manufacturer recommendations, then the manufacturer recommendations. Yeah, but like I said, so there's sort of all these different properties of the cell holders that were semi-arbitrary, and then we refined them through FEA, but they sort of started arbitrarily, and then they sort of were an intrinsic element of the design with an arbitrary value that was only refined afterwards. And so it might be better to like from the beginning think and say, okay, well, how does the thickness of this affect its manufacturability? How does the thickness of this affect FEA? How does the thickness affect all these different things? So that includes stuff like your cell spacing, your lip thickness. When I say lip thickness, I mean this thickness typically. Because of the idea that you have like this lip that sticks out over the cell that sort of like keeps it in place in this direction. And then the thickness of that lip, I think that was like FEA driven eventually.
So the cell holders that we were initially trying to design, like the first place we started is by looking, you can buy like off the shelf little like basically tileable individual cell holders, like a little square that holds one cell. And then they have like little things that you can like connect them together to make like a pack of any size. And we were like, oh, let's just do that. And we'll glue them all together. And then Hess, the company who bonds it, was like, no, that's a terrible idea. You should never do that. But like that from that off the shelf design is where we got most of these numbers of like, I think it's like the lip thickness he's talking about is like 1 millimeter thick. And I'm pretty sure that's where we got that number or value. So, and same with like the thickness of the whole cell holder. Like, yeah, these were all like affirmed by FEA, but like,
why is it not 20?
Exactly. As a starting point, like that is where it came. So it's somewhat arbitrary.
Yeah. Cool. And obviously for the current designs, because the fact that this is also our first year doing a battery pack, obviously there was like a super long, complex design process that we have to go through because it was obviously getting constantly blocked and revised by other designs as we were, moving through doing different cell configurations, as we were figuring out bus bars, as we were doing wiring, all that stuff. So the big topic of improvement that I see us going through for cell holders is a lot of it is going to be mounting related stuff, particularly, I'll go into this more when we talk about the bus bars specifically. But for example, how we actually, mount the bus bars is something that we've done this with adhesive this year, but, we didn't really locate them. We didn't really use any bolts or anything or any actual fasteners. It's all just adhesive, which is great. And then let's see, BMS sense connections. Oh yeah, basically the idea is that this year, like I sort of mentioned earlier, the original plan that we had for our BMS sensing connections was this like uber sketchy run a wire, and then we would like solder the wire to a piece of nickel that we would then spot weld to the bar, and then that was a thing, and then I see you're looking and you're like, what the fuck is this design? So we had this like really sketchy plan, and then we were like, well, we'll figure out a better design if we need to. And then we looked and we were like, shit, we need to have fuses on those wires. And we're like, okay, now what we're going to do is we're going to take a fuse and we're going to conductive epoxy the fuse to the bus bar. And then we're going to solder a wire to the fuse. And then we looked through and we were like, well, now this is going to take a fucking year to manufacture. And every time we rip it in and out, the chances of us clipping these wires and then just fucking ripping stuff off is super high. And so then we were like, fuck it, we're just going to, rather than have wires, let's make PCBs that do the wiring for you because those are rigid and then you can epoxy that to the cells. And it's like this whole thing. But the problem is that obviously the PCBs were complex to design because of the fact that they didn't have mounting and they were not intended to go there in the first place. So we had to make these fucking, you guys see these fucking spaghetti noodles in here that run up and down. Like obviously we have to have these now 5 millimeter wide strips that run up our pack. But ideally we could have just like had a cohesive batteries, like a PCB design from the beginning and just like ran down the side, very, very easy and just like bolted through. But it was one of the things that, like, hindsight is 2020, and if we had thought of that, that would have been great. We didn't.
To a slot that was originally designed for a bunch of wires to go through instead of a PCB.
Fun times. Yeah. But yeah, and so there's all these things where it's like, same thing. Obviously, if we decide to do something like PCBs in the future, then ideally you would have like mounting holes, you have spaces for those PCBs. And like, if they're going to touch the bus bars, ideally there'd be space in the bus bars where you're not going to have random bonds there. And it's the sort of thing that if we decide that we are going to move back to wires in the future for whatever reason, then ideally there would be like designated like thin channels and slots for that wiring. Because we tried a few different prototypes where we were like, okay, what if we give you this like Mondo slot to run wires down? And the problem is that it ends up being the wires also just sort of float everywhere and aren't really well maintained. But if you make like an exact wider width channel and you can like push the wire into it, you can actually manage them really effectively. And so there's a bunch of different options, a bunch of different ways to do it. It's just sort of making a cohesive design from the beginning. Oh yeah, so one of the big sad pain points on the cell holders is that we have a whole bunch of wasted space at the top of it because of the fact that we had two confounding factors that made us. So if you sort of look at the image at the top, you see how there's all this fucking air up here? It's because at the start we had two confounding factors that meant that we sort of had to make it a bunch of space at the top. Number one, when we originally started designing our BMS boards, we put Paul connectors on them because we had them, we were familiar with them. We didn't really see. We were like, okay, whatever, it won't take up too much space, don't worry about it. And number two, the maintenance plugs that we were picking and see where we were going with, the design that we had been given had this like long ass stem on it. And we were like, okay, cool, that stem is already pretty long and the BMS connectors are tall. So there's no reason for us to like shorten either of them because already we have like a number of factors making this top area tall. But then we were able to really easily redesign our BMS boards to make the connector shorter because we were like, there's no harm in doing this. And then the manufacturer that designed the maintenance plugs for us actually was like, lol, get wrecked, nerds. We're not going to make them for you as they batch the CAD. Instead, we're going to just give you some random shit we have off the shelf, and you have to bend it and make it yourself into the shape you want. And as you can talk to Louis and Jacob about, that sucked ass. And it became so challenging. And then also not only that, the maintenance plugs were just so fucking terrible quality that they would like break when you used them as intended. It was so bad. That obviously now we have the situation where we're like, oh well, we definitely in retrospect would be able to move forward for next year's designs with a much shorter maintenance plug and then a much shorter set of connectors in the BMS ports, and the whole battery could be like an inch or two shorter, which would be way better. What's up?
I have two questions.
Yeah.
One, you ever call something like, it sucks.
Well, the main thing is that they're so like nothing against the company. I'll hash on this a little bit more when we get to like the maintenance plug slide set. But it's like the big thing is like they were really slow to work with us. They were very helpful, but it was like they were very slow to work with us, and they're a smaller company. No, this is Royal Connector Solutions. Oh yeah, Royal Power Solutions. There you go. And so the thing is, like, they did go through the effort of like they designed a custom set of connectors for us and all that. Like, if we appreciated the effort and time that they put in, but they also just did a bunch of weird things where they would give us a design and say, oh, use this design. And then after we finished making our battery pack, then they were like, oh, lol, JK, actually, we can't make this. You're going to have to make it yourself, but like, don't worry about it. It'll be fine. And then we tried it and it turns out it was not fine. It was awful. And then same thing, we tried to use their connectors. And like I said, they were just such bad quality. They would just like break themselves just in regular use, which wasn't great. And they were very slow to interact with. Like, we would ask for them and be super slow to respond and super slow to ship us stuff. And that's why we didn't get them until this year, where we finally realized it was an issue. And so it's sort of this whole process that we don't have a reason to go back and like yell at them and be like, make better products. So instead, we sort of just were like, look, we already have a backup set of maintenance plugs that we can make work. So we'll just drop our connection with them. And so we just basically ghosted them. And we're like, hey, we'll still put their logo on the car because they still did give us money, but like their products were not of a good enough quality that it's worth us using. And we don't want to like actively build animosity. I don't think so. Oh, okay. Yeah, so all that's wasted space. Ideally, you'd be able to sort of move all of that out. Oh yeah. Oh, this is something else that I'll talk about more later. Don't worry about that now. Yeah. Oh, and then one of the big things also that you can sort of see is the standoff height. So here you can tell like these standoffs are actually pretty tall. And if you look at the back, you can even see that like the standoffs on this side, for example, are pretty flush. They're pretty short. Like if you look at it from the side, it only takes up like a few millimeters. But on these sides, they're really fucking tall. And that ended up being because of like a confounding set of factors on bolt sizes and nut sizes and the materials that we had and the bus bars that we used. Yeah, that's what I mean. Like, those ones. That's what I mean. Like, there's a whole bunch of factors that went into why they're that tall. But obviously, like in retrospect, having them be this tall does end up wasting like a moderate amount of airspace. Ideally, yeah, it does end up wasting a moderate amount of airspace that, once you look across all 6 segments, ideally you wouldn't waste that extra 2 inches. And that would be something that ideally, now that we've sort of looked and seen all this stuff and and they've thought about all the compounding factors of how big the battery got. Ideally, we'd be able to sort of shrink it down so all of our sides only have these really short standoffs. In the future, would be so that'd be great.
I think one thing we can do with that and back to the box design is that you can see that it's kind of difficult with the hole pattern in the box to get it right up next to the, especially for the side that has the shorter standoffs, to get those holes to actually get airflow through there. And that's kind of the space that we care the most about getting airflow to, is like across the top of the cells and across the bus bars. So if you can come up with some kind of like novel solution on how to, with decreased standoff height, still get like significant airflow across that area, that would be like very beneficial.
Mhm.
So
I also have some slides talking about how it could be possible to design bus bars that don't need active cooling. It's just more of you have to make them really fucking big, and so that's the trade-off.
Why are they not symmetrical?
Like, why is this taller than that?
I feel like it'd be symmetrical.
I think it's because, so the way that the voltage zigzags through, it has to go across the bottom. And so we have a big thick bus bar across the bottom on the side that's taller.
Yeah, like if you actually look, and like everyone else can see, you look here at the bottom, you see how there's one long sticky boy at the bottom of this, like a long silver strip. But alternatively, on the other side, we do not have one, just because of how the voltages in the directions of the cells work. You only need that on one side. And because of the fact that all of the current of the entire battery pack needs to flow through that one strip of metal, we need to obviously make it quite thick. And so that's sort of the downside of it. Since that needs to be super thick and then it has bonds on top of it, you then need to add elements. And then the same thing, I do remember there was some of the reason that we also have a bolt that sticks out here, and then you can spend like $12 on a singular ultra low profile bolt, or you can just make the whole thing taller and not worry about it. But ideally, in the future, we would be able to sort of take all these factors into consideration and say, okay, well, maybe we shouldn't design packs that have thick bus bars like this, and maybe we should design packs that have bolted connections that are sunk in, so that way we don't have to deal with the bolts stick out like that. Because remember also, by rules, all of the connections in the battery pack that actually conduct like battery current are officially critical fasteners. And for anyone who's familiar with your rules, all critical fasteners in the battery pack, number one, have to be positively locked. Positive locking essentially means if you have some form of vibration in the vehicle, that fastener will not be able to untwist itself. That could be anything from a lock nut to, fucking 3D printed things that go around it to make sure it doesn't come loose, to safety wire that goes around it. Make sure that one bolt won't be able to loosen because it'll tighten another bolt. You could safety. We literally thought about safety wiring the bolts with like nylon. We didn't do it, but we could have. But yeah, stupid ideas. But yeah, and so that's sort of one of the high level things. That there's a lot of things in retrospect that we could have done better, and especially we've now seen that like you're slowly starting to see this story of, oh well, because of the fact that we're building a first generation battery, we're not going to worry about trying to make it really dense and really small, and instead we're gonna push a little room here and a little room here because it makes it easier, it makes the design easier, and then now you've sort of seen that creep expand out to the larger battery pack, where you have this really big battery that struggled to fit in the frame, and then we had to really shape the container to just barely fit, and you ended up having all these issues and all these. So yeah, ideally what we'd be able to do is be able to really take from a fundamental look and say, look, okay, cool. We've seen all these problems, we've seen all these issues, and we've seen how this can really creep out to affect the larger vehicle. Let's try to sort of refocus and pull it all back in and take out all this empty wasted space. Yeah, so one of the things I'll talk more about in the slides that it looks like I won't get to today, because we're already at 6, is the idea of optimizing your cell packing geometry. So one of the things that we do in this pack that I'll talk about more later is the fact that we use what's called hex packing. It's basically a honeycomb structure that you can see in the battery pack. Our battery cells aren't lined up like in a square grid. Instead, they're lined up where they're sort of going along these hexagonal shapes. The reason we do that is because unless you're doing like a very small battery pack that needs to fit in a square space, you can actually get more battery cells for your space. And like even in this rectangular shape, you can get more cells in there if you pack them diagonally. One of the big things that doesn't matter as much with a battery pack that's this shape, because one side isn't significantly longer than the other, but would matter a lot if you had like a long and skinny battery, is that if you look, you see how on the sides it's sort of like zigzagged in and up, but then on the top and bottom it's totally straight. You actually find that from like an efficiency perspective, if you have a long and skinny battery, it would be more efficient to have your battery go this direction, and then you're able to really push it up all the way to the edge, and you only get that zigzagging of like that wasted space at the end. Whereas if you were to take your battery and stretch it up this direction, you get that zigzagging and that wasted space all the way along the side, which is really good. So that only, like I said, that only really matters if you're once again trying to do a rectangularly shaped battery with hex packing. And it's like very long and skinny, but that's something that most battery packs do end up being long and skinny. So this does end up having quite a bit. And ideally for like future battery pack designs, if they do end up being longer and skinnier and using hex packing, ideally we would abuse that property of that. You basically only have the zigzaggy bits on the ends, and you're able to do flat faces on both sides. Because then you can get more cells in more smaller space.
Then you can also do a cathode.
Yeah. And this gets back into the question that Drake asked earlier, which is really nice, is the fact that we actually don't have to do like, rectangular shaped battery packs. We did them because we, in our engineer brains, always think of rectangles because rectangles are easy. But if you could think of a really well-shaped battery that efficiently uses it, you actually think if hex packing is so efficient, ideally all of your angles would not be 90-degree corners. All of your angles would be 60s and 120s, and you would make like more of a parallelogram shaped pack or more of like a trapezoid shaped pack. Would in theory be sort of the most efficient way that you could pack cells in there, because you don't have any corners, any edges that are losing volume, because you're always really efficiently cutting into exactly the shape of the cell.
You mean a trapezoid pack for just one of those?
Yeah, for like one segment.
How would you pack those all together?
It would depend on the orientation of the pack, and so that's yeah, and that gets into the larger complexity of designing a segment. Is that like obviously you can't just design a segment in isolation. You have to design a segment that can then plug into other segments, make sure the polarity is right, and make sure you can design bus bars that actually allow them to connect together. And then obviously, like I said, there have been so many pain points with the cell holders, whether it's meshing failing, whether it's 3D printing, whether it's material testing, so much stuff. If you have any more specific thoughts about it or questions, you can always go ask Louis. He is really happy to talk about it and loves being on Formula. Yeah, he does. Confirmed. Sometimes. Okay, so yeah, obviously these things are going to get progressively like they're going to have probably less commentary as we go. But anyway, so bonds. Basically, obviously, as you know, the bonds are the things that allow us to actually connect from the battery pack to one of the cells to the actual bus bars. And obviously, it doubles as this overcurrent protection. The main requirement from it is really just that it's overcurrent protection and it can conduct electricity from the cells to the bus bars. Wow, really simple requirements. Our current ones that we have selected is we are using on every cell, you actually can look at it and see it on the pack. We have two 500 micron aluminum bonds, and those are bonded by Hess Mechatronics. They do that as a sponsorship for us and many other car teams. If you go to my document called Important Email Addresses, you can find the emails for all of these people. But yeah, the idea is that, and so this gets to the interesting point of why our bonding and our overcurrent protection doesn't really make sense, is that based on our empirical testing and based on the test data that they presented to us, each of these bonds can handle about up to 70 amps before it will fuse. And since we're doing two, that means we can handle about 140 amps per cell. If you think about it, our cells are rated for like 45 amps per cell, maybe 90 if you're lucky. And this can do 140, which means it doesn't fucking protect the cell at all, which is great. Yeah, the main... Yes, and that sort of jumps into the higher level idea, is that the rules doesn't specifically, at least from our interpretation, doesn't specifically say that the battery cells have to be protected with overcurrent protection that actually operates correctly. Because they say that if you have, basically, they say if you have a non-voltage rated fusible link, which is the like technical term for a bond, then you already need a secondary overcurrent protection for the whole battery pack. So basically, you just need a fuse at the end of your battery, and to make sure that if you short the battery, that fuse will pop way before the cells internally. actually that fuse needs to be 1/3 of the current rating of all of these bonds together. And that's actually why for us, why we did 2 bonds in parallel, is because if you do the math out, we have 4 cells in parallel, and if we have 2 of these per thing, 140 amps per cell. That means if you do 4 in parallel, you get up to 560 amps total that the cells could source. And then we have a 175 actually, but 180 amp fuse on the battery pack. And that is exactly 1/3 of 560. And the rule specifically says you need to have a fuse for your battery pack that is 1/3 or less the current rating of all their fusible links. And so that's why our overcurrent protection in the individual cells doesn't really make sense, because we had to meet that 1/3 rule from a larger battery pack. But yeah, like Joshua sort of highlighted, there's very little risk in our battery pack that you're going to have like an overcurrent event with the cells. It's most likely the cells will be normal or they will be short-circuited. And if they are short-circuited, these bonds will definitely work. So not much of a concern.
But it's just a single one, right?
In our particular situation, because of the fact that we have 2 bonds, we actually have like a single fault redundancy situation, which is great. Is that since our cells, we are never going to draw more than about 45 amps per cell in our battery pack. One of these bonds could completely break off and we would never have a problem, because the fact that the other bond can still do up to 70 amps. And like I said, we're only going to go up to 45 per cell anyway. So because of that fact, actually half, like if you were really careful, you could take exactly half of the bonds out of the battery pack and it would still operate as intended. Wouldn't be rules legal, but it would still operate totally fine without worry. It would just be, yeah, if both bonds on a given cell broke off, then yes, you'd have to replace that segment or rebond it, but you could just ship it back to test and they would rebond it. You had a question. God damn.
Why do we need 2 bonds again?
So I can walk through the math really quickly. The idea is there is a rule. That rule says that if you use these like sketchy piece of metal type bonds that we use, where it's like a bonded thing, if you use that to do like the current protection on your battery cells, that the total of their current protection has to be 3 times a fuse that you have on your larger battery pack. The idea is like if you imagine you have your battery cell, and another battery cell, and like another battery cell, and another battery cell. You have like a fuse on each one of them. And so you have like a fuse on each one of them, and this is rated for 140 amps each. So this is 140, 140, 140, and 140 total. This can do 560 amps through all of this in terms of like the bonds capabilities. And since they can total up to 560, the rules then says that when we combine all of these together, this all has to go through a fuse that is equal to this. So 560 divided by 3 or less. So if you do this math out, this is 180. So it has to be 180 amps or less is the final fuse we have. And in our battery pack, to be able to achieve the like 80 kilowatt power number that we were trying to achieve, because that's like the rules limit, we wanted to target 180 amp output. Like we wanted to be able to target to output 180 amps of current. And
180 amps, but you're rating of all the cells.
Yep. And so sort of walking on the back, we basically looked and we said, our cells, we know they can handle 180 amps total. And since we want to be able to output 180 amps, we're gonna figure out what bonds we need to be able to put 180 amp fuse in there. And so since rule says 1/3, we multiplied by 3, and then we went, okay, cool. So that means we want 140 amps per cell. And they don't, like, TESS doesn't offer 140 amp bond, but they do offer a 70 amp bond. So we're like, okay, cool, that works. Let's do 2. Done, no problem.
We also did like a decent amount of testing, like we basically sent tests like a copper that we had them bond together that like had rings on bonds at the end. We basically just hooked them up to a battery and tried to see like which configuration, thicknesses, quantity was the most ideal for what we were looking for, like when they blow up, when we
Exactly.
Is also testing that could be carried out further.
Yeah, it's all sort of it's all was actually driven both by like the data sheet that they provide, and then we also we empirically tested all that.
Will we be ready to replace this segment?
We do have something we did mention briefly last time is that if we get into it, the current problem is that we do have the battery cells, but the complexity, cost, time, and effort that would have to go into making more cell holders is quite high. So what we would have to do is if we did have one or more bonds break, the plan is that we're going to bring something like a thin nickel strip to competition. And what we can do is we can then use a spot welder to spot weld that on in place of the bond. While that's not great, generally nickel strips can handle something in the range of 10 to, if you're lucky, 20 amps. And so that still means that while it's not great, we would still be able to output up to, what would that be? Assuming that we're trying to draw them all the same cells, that would be what? 80 amps at 600 volts is what? Yeah. Well, it's because it'll fuse before the bonds would. Because it'll be rated to a lower. You drive slow.
You drive slow, and also we can update the value in the BMS, then it'll require less current draw.
Yep. And so sort of
80
that.
times about 600.
Yeah.
That's like only 50 kilowatts.
Yeah, and so we would have like half of our power budget stripped out of us, which means that we basically wouldn't be able to go at any higher speeds than like 40 or 50 miles an hour. And we would even then past like 20 or 30, we'd be pretty torque limited. So that's not great, but we would still be able to, drive competition and do our thing. So while that's not awesome, and ideally if we had more budget and like, we could get more of the cell holders, we would just have spares. But currently we don't. So that is our best backup plan.
Does that mean you can update the BMS and pass it over? You just throw the card out?
Yeah, no problem.
I mean, we can also just tell the driver not to put the hello card. That would be more.
I'll tell this man he
Yeah,
can't
so-
drive back.
That's like,
Yeah, you electrical people gonna tell me I can't do what the fuck I can't.
I think that's more don't mapping thing than the BMS thing. Less about BMS.
Oh, what's up?
Why do we have like a fuse that sticks out of the cell holder to stop overcurrent? Like, why isn't it just part of the?
So there is a rule that specific. You could explain it.
Well, I was going to explain a different thing than you could.
Oh, okay. No, you explain.
Okay. So well, my explanation was going to be the BMS in the segment actually doesn't have the power of the pack going through it. This is just the monitoring board. It can't disconnect things.
Oh, okay.
And so then the main board can disconnect the entire pack, but not a single cell, and then you can talk about rules.
Oh, love the rules. All right, let's talk about rules. Okay, so basically there is a rules requirement that says any voltage sensing connections in your battery pack need to be fused.
Oh yeah.
Yeah, so there's a specific rule that says that any voltage sensing connection in your battery pack needs to be overcurrent protected. That means you need to have a fuse on it, or some similar device, so like a big resistor or whatever. So that's essentially why we have them. The big thing is that the rules also very clearly highlights is that they say they basically want it to be as close as possible to the source of the power. And so the idea is that if you were to short circuit, like let's say I were to be stupid and put a piece of metal in here and kind of short all the batteries together on this connector. The idea is that they want the fuse to be located as close as possible to the source of the power or the battery cell. And so that's why what they prefer that we would do is that they either have directly connect the fuse to the cell or connect the fuse right there in the immediate first conductor that is connected to the cell.
Right, so was your
Yeah,
question about multiple times fuses or the bonds that are?
Oh yeah.
I guess both.
Yeah, so so
Yeah, my answer was more about the cell level bonding, cell level fuses, and then Chris's answer was about the voltage sense fuse on the sense boards.
Okay, that makes sense.
Yeah, and so that's the big thing. But they want They want there to be they want there sort of be fusing as close as possible to the source of the cell everywhere. And the idea there is that you want to minimize the amount of length of conductors that could short circuit without like fusing or without some kind of overcurrent protection. So they want it to be as close as possible. That's why it's directly there to the surface of the cell, and that's also why it's directly right in there in the strip rather than all the way up in the end.
Air is flowing past the bond, on the side of the bond.
Yeah.
How is air entering?
Yeah. So the idea is that there is a larger box that it sits in. That box has 3 layers of holes with holes that are misaligned from each other. The idea is that it still allows air to flow through it, but you couldn't directly like poke a stick inside. Yeah, there's a box. Yeah, the idea is that, yeah. Wow. And so there's a box basically that it all sits in, and then the idea is that the holes in all of the interior walls are lined up. So air can flow through, air can then flow through the steel wall, through holes in that, through this, out through another steel wall into another segment, so like through its battery pack cell through the key box, and then back out of the other side of the pack. And then we have fans that push it. No.
Like
I mean, unless the pebble could float.
it would have to
Well,
try.
don't we also have water blocking the entrances?
And it was very small, fair point, yeah.
So it would have to be.
It would have to be a very sharp,
It would have to be
very
smaller than
nimble pebble.
Yeah, so your sharp, nimble pebble could get. But yeah, so because the idea is that they do like spray our battery pack at competition, and the idea is that we want to make sure that no water can directly get in. There's a rule that I think it says something like they have like a stick. I think this is called out in tech where it's like you shouldn't be able to poke any battery cells with a stick. And obviously the motivation of that is to make sure that you don't have like the wall of your battery pack right here with an air hole, and then you can just like see the cell. And so that's why we have those like off-shifted walls to make sure that both it avoids high pressure jets of water, but it also avoids the stick test. I don't want to go put my fucking thumb in the battery. Like obviously, these holes are pretty small. But, like if I was particularly malicious and particularly skinny fingers, I could like shove it in there and touch them.
Is it malicious if you're just trying to die?
I don't know.
Because you wouldn't hurt the battery would hurt you.
That's fair. But yeah, anyway, getting back to bonds. Yeah, so one of the thing that we currently design for the bonds is that we use what's called like opposing terminal bonding or negative terminal bonding, which is just the idea that, like I sort of talked about last time, on the battery, you sort of have 2 sides. You have one side with a bump on it, and the whole rest of it, which is all smooth. The whole rest of it is all the negative terminal. That includes, the side and the end. And then the side with the bump is the positive terminal. So the current way that we do it is we put a bond on one side and a bond on the other side, and that's it. But there are theoretical rim bonding designs where you can actually bond both of them on the same side. You can see the positive and the negative there. Just the space available for the negative terminal is so small that it's generally not recommended unless one of your other design requirements requires that you do rim bonding. For example, if we were to liquid cool our battery pack with a cold plate, specifically, we would have to do rim bonding because otherwise the cold plate would be on part of the cell, so you wouldn't be able to bond to the other side. But like, if you did something like an external cooling thing with some kind of thin or heat pipe solution, then you could reasonably have normal bonding with heat pipes that go off the side. So
Wouldn't that free up a bunch of space on one side?
yes, you're correct. If you wanted to build the smallest possible battery pack, let's say your name is Tesla Motors, then yes, that is what a lot of the battery manufacturers will do. And actually, if I go to this slide right here, you can see what a lot of manufacturers do. Is that you have a cell holder that goes around, and then they actually expose parts of the negative terminal, and then they'll bond from a bus bar to the positive terminal, and then negative terminal goes to the previous bus bar. Oh, I clipped a bunch of shit out of this. This pack looks way better than ours. But I clipped out the good looking parts.
Yeah, like right there.
Yeah, that could be us. Anyway, yeah, and so that's the thing is that there are other options, and yeah, if you wanted to make the densest possible pack, like if you were Tesla Motors, then actually, if you walk around at the Tesla factory, you'll even see that they have like images that look like this of their battery packs with all the little bonds on them on the top. If they bond it all on one side, and then they put their cooling solution on the bottom and through the middle.
And also all.
Nope. I mean, you'd need some kind of holder just to like maintain rigidity because you don't want a cantilever load on the cell. But yeah, you would just have some kind of holder or something. You wouldn't need standoffs or anything because there's no bonds. There's nothing over there. Just stuff. We even considered doing single-sided bonding for rim bonding on our low voltage pack, but then it wasn't worth it because it started to get really big for other reasons. So yeah, yeah, obviously the big downsides with us using bonds at all is the fact that, like I said, they're really fragile, they're really easy to break. Like if you came in with your fingies, like obviously this is like 0.5 millimeter thick aluminum, you can fucking like break it. It's very easy. Like don't do that, obviously, but that's why we need all these protection features. They're not robust or strong in any way. And obviously these bonds, like we sort of mentioned with the cell holders, is that there's like a high rigidity requirement. You're seeing a lot of this interplay between the bonds because of the fact that they have great other properties now suddenly mean that our cell holders, which are really complicated, then have all these rigidity requirements, and these rigidity requirements affect manufacturability. All right. And then one of the other things that we'll see more in the bus bar parts is that because of the fact that we used adhesive to, like we used a water jet and adhesive to make our bus bars, a lot of our bus bars were bowed, which meant that they could sort of wobble up and down in the middle. They had weird gunk on the surface, so they didn't actually make good contact with the metal. And the adhesive on one of the packs actually ripped off. One of the bus bars just gone. And so that's the thing is that it's like obviously there are a number of problems with the way that we did it, and if we were using something like spot welding, then that would have been no problem because you can just press and do it. But since with our current requirements, we kind of need to do ultrasonic bonding. These are the downsides that come with it. You need extra rigidity. You need to really fasten your bus bars properly. And it comes with all this complexity of, you can't really just glue it in place anymore. Or you can, but it doesn't work well. Oh, yeah. Well, here's a whole bunch of areas of potential improvement. I sort of highlighted most of these already. One of the things is that our bonding manufacturer can pretty easily just like we can just pick any path of what the metal is going to look like when they make that bond. So if we wanted them to be really, really short and really low profile, they can just do that. We just told them they could make it whatever height they wanted because we were like, our standoff is this high, you can go up to this high, we don't care. And that's why actually, if you look at the side that has the taller standoff, you'll see that the bond they're actually like taller than they are on the other side. And so they'll like more of like a go up and around rather than just up and straight down because it's a little easier for them. But they can control exactly what that shape is. And so if we really are going to try to push it in and save this extra, pounded inch of space by pushing these standoffs down, then we would have to make explicit to them, be like, hey, you have exactly this much height to do your bonds and you have to fit it in.
One thing to keep in mind with all of this is that the machine that they use to make these bonds does take up a certain amount of space, and you need to. They sent us a CAD model of like what that machine looks like, and it's fucking big. So you need to make sure that like with whatever your cell holder design is, and like your bus bars and your bonding considerations, you have to make sure that like the head of that machine can actually fit in and make contact with the cells or with the bus bars without actually like colliding with something else. And also, we're hopefully going to have a design review with them sometime this week because they said they were going to reach back out to us like they have it done and they didn't. So I just sent them a reminder email. So if it's fine with Chris and with them, then if anybody wants to just like sit in the back and just like listen to that and kind of hear about what a design review for a battery system looks like, you are more than welcome.
Yeah, something that we maybe should worry about next year, it's fine for this year. If we have different length bonds on the two sides, I think that can actually affect fusing current.
You're correct.
Like
It does.
shorter bond,
It 100%.
fusing current, which means that now we have different amounts of fusing current on each side.
Yep, that's
which
correct.
is a little weird.
Yep, and that actually would definitely be like a great thing to focus on. Is obviously our fusing currents don't really matter anyway because we're all doing this hand wavy. But yeah, definitely in the future, if that's something we start to refine and improve, then yeah, definitely try to make it consistent across the pack would be a great practice to follow. So yeah, lower profile bonding, rim bonding, we already talked about that. That's where you bond on the same side, so the opposite side. Hess doesn't like it because, like I said, there's not a lot of space and it's harder for them because the chances that they fail and miss is way higher. but it does mean that you could dedicate a whole side to cooling or some other consideration. Some of the best teams that I know do single-sided bonding, like Carnegie Mellon. They'll do a pack that has the PCB goes on one side and the bonds are on the other side, and they're really. But anyway, yeah. So another thing with bonding is you can actually bond to the BMS sensing connections. So you know how I said that they can bond to stuff like copper and aluminum? Well, they can also bond to PCB surfaces. So rather than us having to do this sketchy thing that we're doing this year, where we use like conductive epoxy to epoxy a PCB with a contact pad to a piece of metal, Hess just directly says in their documentation, they're like, yeah, if you want, you can just put a PCB on your board, whether you bolt it down or you adhesive it down, don't care. And then they can, just like they can bond a cell to a bus bar, they can also bond a bus bar to a PCB. And so instead of having to do all this sketchy epoxy shit, we can just like have it get all bonded and assembled for us immediately, which would be quite nice, way easier, and it's definitely something I'd recommend, assuming y'all choose to actually move forward with doing PCBs next year for the testing. Yeah, would be sick. Well, and that gets into the larger idea of like if you cannot have daughter boards and if you cannot have sense PCBs and if you can just have one BMS PCB and then you could bond straight from the bus bar to the PCB, that would be sick. But that's hard to design because then it has to be really long. Anyway, so yeah, the next thing is that one of the things that we didn't really bother with this there is we sent them like a diagram that was like, hey, this is how we want you to bond it. But they sort of like, since our bus bars kept giving them issues being able to bond effectively, it meant that a lot of the bonds on the actual packs are not where we said we wanted them to be. And we kind of were like, yeah, we're kind of loose about this. Like, it's fine. Don't worry about it too much. And they just sort of did whatever the fuck. And while that's totally because we told them they could do that, it's also annoying because it meant that when we went through and we tried to put these sense PCBs in afterwards, we now have a few PCBs that just because they put bonds in weird places, or if the bonds fail, we now can't fit the PCB on there, and we have to actually wire it manually because the PCB literally doesn't fit. Or you could fit half the PCB, but then there'll be a bond in the way halfway down, so you could like cut the board and rewire it. So yeah, and so that's the thing is that you have these weird things that come up because we weren't really strict about how they bonded it. So ideally, in the future, we would have a much more concerted plan about exactly where we're going to be running stuff, where we're going to be routing stuff, and then tell them, okay, you're going to bond exactly here to here, exactly here to here, and give them a very strict, clear model.
Why would bonds fail?
Bonds can fail for a number of reasons. Obviously, there's the fusing element of like if you run so much current through it, pops. The big thing, do you mean why it will fail to bond or why it will break after it's bonded?
Why would fail to bond?
Yes. So when you try, like, let's say you have a bus bar that was bent when we manufactured it, so it's actually like formed. That means that when we epoxied it, chances are the center didn't actually epoxy and just the ends epoxy. And then as they try to bond it, since it's ultrasonic, it'll actually vibrate up and down. And because of the fact that it's vibrating, it's not generating the heat that they want to generate, and it's not actually making good contact. So they'll try to bond and they'll just fucking spaghetti noodle up into the air. And you can actually, I think you can see a video on their Instagram of bonding our pack. I didn't look, but they asked me for permission, and I said yes. So if you find the Hess Mechatronics Instagram, there might be a video of our pack getting bonded. So yeah, because they asked, and I said sure. Anyway, yeah. So all that with the sensing boards would be very useful, very helpful, very important. Yeah, bonding diagrams, all that. And then obviously a big thing that I'll talk about more with the actual bus bars, but a big thing that does sort of come into effect with the bonds, like I talked about, is, like I said, we sort of epoxied these bonds on this year, and that's led to a lot of problems where they don't really make good contact, and they're warped, and they rip off, or they wiggle. And also, like, it doesn't locate them. Like, if we just epoxied them in place with, like, our fucking eyes, and that meant that they weren't always in the correct places. So ideally, we would move over to more of a mechanical fastening approach, where you actually are using, like, a bolt to bolt the bus bar into place. And that's one of the things that I clipped out, is that if you look at this bus bar in the real image, it's actually a bolt frame to hold it in place. And if you go online, most of the pictures you're going to see of battery packs use bolted mechanical bus bars in place. And that's actually what Hess very strongly recommends. They were like, bolted bus bars are a way better approach. Definitely do that. Only do epoxy if you like have to use epoxy. We're just That's so sad. Oh, fine. There's definitely maybe they'll just use it in promotional material. They were like, can we use yours for all of our socials? Like, sure. Cool. Anyway, Yeah, and also one of the things that Louis mentioned earlier that I want to point out is there's a link on here to a super duper uber helpful guideline doc that's like 40 pages long from Hess that explains everything you could possibly want to know about bonding. So like how to pick materials for bonding, how to design your bus bars, how to design your cell holders, what your glass content should be, what your material type should be. They just explain all of that in this super duper uber helpful document. That I'm not going to click on right now, but I could. And definitely, this is one of the things that, after we went through and designed our battery pack, we actually looked at this year and we were like, wait, we're so stupid. There's like a bunch of really useful shit in here that we like reverse engineered ourselves. And we could have just looked in the document, read it, and they sent this to us last year. And we just had sort of glossed over it because they like presented it to us, but they skipped through all the slides and they didn't really highlight most of it. And then we looked back there and we're like, oh, this actually has really useful stuff. And so definitely, if you're going to do battery pack stuff, this is something that you should be very involved in. Whew. All right, we're on to bus bars. Let's see, what slide are we on? We're on slide 48 out of 82. Okay, bus bars. Obviously, wow, the electric connections. These are getting into the sorts of things where now we're starting to get a lot of overlap between the stuff that I've already explained when talking about other parts. So I'll sort of jump through it pretty quickly. Obviously, it has to be able to withstand current flowing through the battery pack and be able to actually distribute current between our cells as we draw from them. They have to not overheat. And then obviously they have to be rigidly mounted enough and made of a strong enough material that you can bond to them successfully. For example, Hess actually recommends that you don't bond, like, let's say you're looking at picking on aluminum and you're going to try to bond to the aluminum. They actually recommend certain types of aluminum that are harder, even though they have high purity, they are harder grades of aluminum, specifically so that way they can bond to it effectively. Because they're like, yeah, if you give us 1,000 grade aluminum, we'll have issues because it's going to be too soft. But if you give us, what is it, it's like 1145 aluminum, that will have a similar level of purity, but it'll also have a stronger surface that will be able to bond to effectively. So, yeah, blah, blah, blah. Also, a big thing for a requirement of bus bars, it should be flat. I didn't think I'd have to specify that, but the water jet is a strong motherfucker, and it bent the fuck out of most of our bus bars when we cut them. And we didn't really notice, we didn't really think it was going to be a huge issue. And then obviously ended up causing a lot of problems when we were bonding and causing a lot of problems elsewhere. And
with the people who laser the bendy thing.
that's the plan. Yes, we have a dude who's one of our alumni named Brendan DiVincenzo, who is one of like the high up dudes at like a big laser company. And what he can do is he can just laser cut all this for us. And unlike the water jet, which has to shoot ultra high power, like garnet based water at stuff to cut it, and then we'll bend thin things. You can just use a laser, which has really high resolution, is super fast, super easy, doesn't fuck with the surface finish, and it's great in every way. And so that would be sort of, yeah, and zero force. Like, you can do smaller internal geometry, you can do crazy shapes. It's way faster. It's literally like Louis has a video that he probably sent to the Powertrain channel where it's like, 1 second, done, bus bar, and it's super fast. And so it definitely would be sort of the recommended approach moving forward in the future, because we had a lot of issues with the water jetted bus bars. And then also the last few things about bus bars is ideally, obviously, you want them to be low cost and easily manufacturable. And this is sort of getting the idea of sometimes you can have designs of bus bars, particularly once you get into weird segment designs, where the bus bar will be super gnarly, but it'll require like 9 bends, and those bends will all be impossible. And so it's just making sure you have a bus bar that's actually physically manufacturable. And obviously, ideally, you can make them cheap because right now they're made of copper, and copper's pretty expensive. Specifically, Hess said that if you make them out of copper, you have to do electrolytic nickel plating on them. Something about blah 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 blah, combination of corrosion and the ability of the actual aluminum to bond to it. And so they were like, yeah, you have to do electrolytic nickel specifically, and that has become a huge problem for us. Electrolytic nickel plating is actually something that most companies don't want to do if you're a stupid group of students that want 100 things plated. They want to talk to you if your name is fucking Ford and you want to plate 100 million things. And so that means that most companies won't do that for us, and we actually had a lot of problems being able to source bus bars. And the strong recommendation is that you would move over to something like aluminum, which, like I mentioned earlier, you would just want something that's a very high purity alloy, so something that's as conductive as aluminum can get, but also has that surface hardness that you need for effective bonding. Blah 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 blah. Our current designs for them are kind of naive. We basically made a bunch of rectangles. and then we made them out of copper, and then we found one company that was willing to do electroless nickel plating, and then they proceeded to tell us to fuck right off after we worked with them. So we're not going back to JMD Industries. But yeah, so we found one company that was willing to do the electroplating for us, and that's how we got the bus bars from the current pack. But sadly, in the future, we're probably going to have to pivot to aluminum simply because it's more easily sourced and more easily, much easily sourced, and you don't actually plate it. Definitely lots of great properties there. So a few of the other things for the bus bars I do kind of want to harp on is that in our battery pack, if people know what I mean when I say something is or is not located. Cool, you know what I mean? So locate a thing. Cool. Yeah, so for anyone that doesn't know, the idea is that like you have some kind of feature that rather than just me saying like I'm gonna put this marker in space, I like put it like up against the thing to like actually define, okay, this is made up against a particular surface, and that locates it in space. And the idea is you would have those features on a bunch of different directions to make sure that it can only have one space that it fits in. Something like a bolt, especially like a shoulder bolt, could effectively locate holes and bus bars. But ours, we didn't really locate anything. We kind of just like put them on there and then epoxied it. And so that meant we had a number of problems of they weren't all necessarily lined up perfectly. And they obviously the epoxy, while great, is still just an adhesive, and so it can have issues securing things.
The way that we located the bus bars on there is I measured it with like a ruler, and then I'm pretty sure I marked it with a pencil, and then put it in. Versus like this is talking about like shoulder bolts, they're very highly precision machine bolts that are like very tight tolerance. Look,
How much craft do you think the pencil is out there?
I mean, I rubbed it off with my finger, so hopefully.
But yeah, so yeah, obviously going through the sort of improvements, I already talked about this. Move to aluminum, it's generally easier and better in every way. But obviously the big downside is the fact that aluminum is not as conductive as copper, so you need something that is physically larger volume to conduct the same amount of current. Specifically, aluminum is 60% as conductive as copper, so you end up needing about 60% more volume to conduct the same current. But that's also fine because of the fact that from a weight perspective, the battery pack, the copper is approximately 3 times as dense as aluminum. So even if you need 60% more volume of aluminum, you actually will have a lighter overall battery pack if you do bigger aluminum bus bars and smaller copper bus bars, because of the fact that the copper is so much denser. That means you could make a lighter battery pack too, which is super cool. It would be cheaper. Yeah, so it would be cheaper and lighter, and that's great. But yeah, obviously the downside that Joshua highlighted really well is the fact that you still would need to go up by 60 or 70% in your cross-sectional area, which means that your battery pack is getting bigger volume-wise. And if you don't necessarily have the space in there, then that can become a big constraining factor. You now need to have this really big hunkin' bus bar. And the way that I sort of recommend it is, like in here, obviously we made them these super thin strips. The recommendations I've seen on most battery packs is they just make them fucking as big as possible. They will make it cover the whole goddamn surface. And that's okay, because of the fact that it means that when you make it super big, it means that it's better conductivity and it has more thermal mass. So it actually won't heat up as quickly and it can radiate more effectively. So it will actually, you can get into a situation where if you make your bus bar really big and fill up a lot of space, then it will actually never overheat when you're running it normally, and then you don't have to actively cool it, which would be super cool.
When you mean cover up the whole space, like, and all of the whole thing.
Yeah. So that's one thing that actually, if you look at like battery pack design, like if you go onto your phone and you say like you Google like a bonded battery pack, you'll find really 2 sets of results. One will be the strips like you see us doing, and then another set will where you basically have the entire surface is covered in available like bus bars, and you just have these tiny gaps between them, and that's it. And so that's a relatively common solution. People go through and they'll basically fill all of the available area with the like. So there we go. Yep.
So like,
Here's what we're doing in pencil. So like you can see,
Yeah.
it's like a big sheet of with holes in the bottom.
Yep. That's all.
Also a little bit different.
Awesome. Cool. What's up?
People of the bars versus how they're bonded.
Ah.
That they're in parallel versus in series.
Nice. Nice. Yeah. Cool. So yeah, I'm gonna keep rolling. Yeah, obviously, like I talked about, aluminum is generally great because it's way easier to source, and it does have some potential upsides in terms of it has more surface area, so it can actually dissipate heat more effectively. As you're sizing it up, it's going to be generally lower cost, easier to source, still same level of difficulty of cutting it. And that's also the recommended option from Hess. Hess actually is like, unless you need copper for some space reason, you should do aluminum, and we just didn't know that because they didn't tell us. But like now that we know that, we should probably stick with aluminum as a recommended option. For other improvements, obviously, like I talked about mechanical fasteners, I don't need to harp on this too much. Adhesives have problems. The big thing that I want to say is super weird is that with mechanical fasteners, they actually recommend bolting through the bus bar, through the cell holder, through the whole pack, and then putting a nut on the other side of the other cell holder, and you literally bolt through the entire pack. That seems super sketch to me, because it's like now you have, these cells are like 3 inches long. You now have a 3-inch long bolt that is holding your whole thing in place, which to me sounds like you're going to get lots of shear and slip and weird forces. But that's what they recommend. They're like, yeah, that is the most effective way to do it, is that you just bolt through the whole fucking pack and like hold the bus bar on that way. That's the greatest way to do it, especially if you do like a taper and a tapered bolt head, then it'll like fully locate it more than something like a regular threaded bolt through a clearance hole would. So
That also puts challenge.
what do you mean?
As long as
Yeah, well, yeah, so that definitely presents. Yeah, so that definitely presents the scary situation of, you're right. Number one, that means now you have your battery cells, and then you have a conductive bolt that's going right in between them. And then, yeah, you now have the bus bar. That voltage is now present on the other side of the pack as well. And so you now have all of these new confounding factors, like, okay, well, now I have to be careful that, like, I now have all these critical fasteners that now suddenly could loosen. So I need to make sure I have lock nuts on all of them, or something like Loctite, whatever. And so I have now all these moving parts, all these individual parts that all of them during assembly could fall apart. And then you're right, same thing. You get this larger thing of now these voltages are all on the wrong sides. And you have to be very careful about where exactly you're putting the bus bars. So mechanical fasteners have a lot of great advantages, like I said, over adhesives, but they do also have additional new problems that come up. If you're someone who's very into 3D printing, you may be familiar with the idea of a heat set insert. And Hess, to us, we were like, oh, heat set insert seemed like the awesome solution to this. You don't have to bolt through the pack, and you can now actually directly, nut bolt straight into the cell holder. That seems awesome, but Hess was like, no, fuck you. Don't do heat set inserts. They said they've had big problems with it. Particularly, they've said that because of the fact that a heat set insert specifically melts the plastic, they get a lot of like doming on the side, which means that when you bolt the bus bar on, the bus bar actually doesn't sit flush to the surface. It sits with mount a little bit above it, and then you get the exact same problem as with our advanced bus bars, where it'll just wobble in the middle when they try to mount it. Obviously, if we could make a way that guarantees that is not a problem, then that might be okay. But Hess definitely said they were like, yeah, this is something we've had historical issues with the past of any form of heat set inserting, and they generally recommend to not do it.
really the problem is just have the actual that hole inside a little bit, so you have like a little bit of appearance on top.
Yeah, and so that's one of the things that that was my immediate jump in. It's just like, well, can't you just sink it in a little bit then and then do that? And so the idea is that when we're chatting with them, I also wanted to ask them a few questions, be like, hey, how does this work? What are your thoughts on this? Because definitely, if we could find a way to use heat set inserts on one side, that would be way better than having to bolt through the entire pack. Definitely way better.
For how you basically adhere your cells and your cell holders together, is that like a supposed to like you can use the courses to actually like glue the cells in?
It does not explicitly say in the documentation.
But that can be.
That sounds like from their presentation, that could be a good assumption, but it's definitely something that it would be probably best to just hop on a call and ask them. Wow, imagine it's almost like we're talking to them in a few days or soon. But yeah, and so that's the thing is that, yeah, definitely hop on a call, ask them these questions, and then see how it goes. Yeah, and obviously, like, I don't need to rant about all the stuff we talked about before with why mechanical fasteners are awesome and why and why adhesives are bad. But yeah, generally it's this whole idea of the adhesives can break, they can fall off, they can make bad things. The bolts actually like innately are locating and they're much more rigidly securing things. The chances of failure during bonding is obviously far lower because like, your adhesive is just gonna rip off, but your bolt isn't gonna fucking rip out of the pack. And then Oh, the big thing that they do also highlight is that especially if you have these long bonds, like you see how we have these like long skinny bars, they're like really, really, really do not just put one bolt on either end. They've seen a lot of behavior where the material itself will actually flex because the fact that you bolt on either end is basically like a banjo string. You're just fucking strumming it and it will bow a little bit enough that it'll have bonding issues. And so they recommend, yeah, you should be putting like many fucking bolts in there to hold it in place. Basically like as many as you can fit. So that makes sense. It gives it a very nice, secure, locked-in connection, which is cool. And then, yeah, obviously this comes with the other additional problems, like I already mentioned, of complexity. Now you need to figure out, okay, cool, can you do a heat set insert? Do you need to bolt all the way through the pack? How does that work? How do you positively lock it? Now you have all these things flying around in your pack. They come bolted. How does the BMS sensing work with this? Could you put a ring terminal into one of these connections? Could you bolt a PCB? Do you just ignore it and bolt the PCB separately? Lots of new questions pop up here. And those are all fun things I'm really excited for y'all to explore next year when I'm gone. That's not my problem. Yeah, I already talked about laser cutting. I don't think I need to explain it. Laser cutting is awesome. It applies no force. It has a way better surface finish, and it's super fast and super easy. Just don't water jet them. The water jet applies a lot of force. It bends them. It causes fucked surface finishes, and it gets dirt and shit all over your bus bars. Just use the laser. So
This might not be the right, that's the question.
that's okay.
Can you go over like at the end of the day, what the right order to consider these? Like, I feel like there's a better way to like go through the design process, right? Like, do we start with cell holders or do we start with like, I don't know, the very nuanced?
So yeah, so there's two elements here of if in the most ideal world, yeah, like Louis said, you would kind of like everything simultaneously. Obviously, that's not feasible. So usually the best way to approach it is you sort of the stuff that it looks like we won't get to today for time reasons, but is in the latter parts of the presentation, is how you do your segment structure of basically how do you package the cells within a segment, and then how do you package the segments within the car. That is fundamentally like the biggest, most important thing. And that's where you start. And then the idea is that then once you have the idea of what that's going to look like, you then do a first pass going through and saying, okay, based on our knowledge of all the other things, of the sensing connections and the BMS mounting and all that, like based on all the other things, how do we tweak and modify those existing large architecture designs to fit in and solve these problems? And if something is like a major issue, they might have to say, fuck, for that reason, I have to now go back and restart my like larger cell configuration within a segment. Yeah, it's like you do the big structure and then you trickle down, but then the idea is that you should mature all of the designs to the point where you like know what each of the things is going to look like and work like. And then once that's done, you can if any of those are like hit a real problem where it's like, oh, this completely fucks the design, then you sort of do have to go back to the drawing board and say, let me restart. Because like we sort of talked about this year, if you try to design half of it and then slap stuff on top, you will make a thing that works, but you will end up doing twice as much work as if you just spent longer on the design, really making it all good, and then just make everything at once. Because fundamentally, manufacturing a battery pack, while it's a lot of effort, isn't a monstrous amount of time and work. It could reasonably be done in like a month or two if you put all the design work in. Now we've spent months and months and months designing things to put band-aids on top of a design. Yeah.
When we respond to the question a little more of like which order of things to consider, I think the way that we approach it, and I think that Steven is a good way to approach it, is you start with the constraints of like how much space do we have in the frame, and that'll kind of guide basically a lot of your initial designs, because you can't make it big space. We also want to use as much space as you have, and then also like what your like electrical constraints are. So like what your configuration of like number of cells, kinds of cells, series versus parallel, and stuff like that. And as you kind of play with what those different configurations could look like, you'll come up with like a bunch of different designs based on these constraints of like space constraints, and then you can work on different like packing structures and kind of then start to narrow in of like what like an initial cell holder. Starting with like your electrical and overall space constraints are a good place to start.
Definitely. Cool. All right. Well, what's up
I had a question about the nuts. So is that like
about these nuts?
yeah.
Wow.
Do they like stick out of the pack and like you tighten them with like a wrench, or is it like active in some sort of?
Don't know. They don't give you an example.
Okay.
If you want, you have access to these slides. You can read through the design guidelines where they say it, and they're just like, yeah, you should bolt all the way through the pack, and they just keep going. It's like, what?
And then another question I have was, can you start off with like, so we the buffer design is like kind of naive, like it's just rectangles,
They're
but mainly just because like they don't have like mechanical fasteners, or is there something besides like
Well,
it being just rectangle that can be improved on?
Yeah, it's like the whole idea of like we made them out of copper and then plated them and went through the whole expensive long process of plating them when fundamentally we probably should have done them out of aluminum from the beginning. And the fact that we made them rectangles and the fact that we didn't locate them and we didn't use fasteners, it's like a whole host of we chose the wrong material and the wrong shape. Like, we didn't effectively use our space. And so that means we're generating heat unnecessarily. And then now we have to actively cool them. Whereas in theory, if you had a big enough volume, you would have enough mass and a low enough resistance, you wouldn't generate a lot of heat. And you would then I was like, you can do the calc out. If you make a conductor wide enough, the pack will run out of energy before the bus bar overheats. And so ideally you would just always be in that area where it's like you never overheat because you don't heat up fast enough, even with an adiabatic system. And sort of that would be the optimal plan. Yeah, anyway, talked about laser cutting. Laser cutting is awesome. And then sorry.
Why do we, like, this is going back a little bit, why do we have segments? Why do we just have one, two?
Yeah, so by rules, we are required to have segments. Those segments have to meet two criteria. Number one, the segments cannot exceed 6 megajoules per second. 6 megajoules in watt hours is about 1.66 watt hours.
Meaning
Kilowatt hours.
Sorry, kilowatt hours, you're right. Yeah, about 1.66 kilowatt hours. And so that means that we have these energy limitations where it says, okay, we can't store more than X amount of energy per chunk of the battery. And that's why we have to split it up. Our battery, for reference, is 8.7 kilowatt hours, and a Tesla is 100 kilowatt hours. And so obviously that's why, for us, we split it up into chunks of, I think, like 1.4 kilowatt hour chunks, and then you add those together.
what's like the ideal amount? Like that, I mean, that plays into how much energy we want to output in like, throughout the rest of the car, but how much?
Yeah, let me go to the slides that cover this.
What did I keep the field? So minimum amount of energy that still fulfills all the functions.
Yeah. Yeah. So you got so yeah, you actually got really well to one of the questions in the slides in the 80s. Is like yeah, you're right. It's like how many when you're going into your general high level segment design, vehicle design, like how many segments do you want? And the answer is that there isn't a correct answer necessarily. A lot of the best teams that I've seen are running a configuration that uses like 6 to 8. But we've seen designs that go up to 10 or 12. Obviously the main thing you have to consider is that yes, you have these energy and these voltage limitations that you can't go above 120 volts in a segment, and you can't go above 6 megajoules. But alternatively, obviously, you want to try to make every segment as energy dense as possible because, with every segment, obviously, you now have cell holder, and then you have boxes, and you have a maintenance plug, and you have all this extra shit that comes along with the segment. So if you had expanded out 100 segments, you would now need 100 plastic boxes and 100 maintenance plugs, and it doesn't work. And so ideally, you'd make your segment number lower. But also, if you have a design that, let's say, uses 8 segments, but really efficiently fills the space in the car and is a really nice, optimized, well-cooled design, that could be better overall than a design with 6 segments that is very inefficient. And so that's sort of the trade-off is if you have equal designs, you would go with lower number because you don't want to waste duplicate stuff. But most of the time, you should be prioritizing how do I most effectively fill the space I'm given and meet the functional requirements, and then whatever the number comes out as, the number comes out as. That's what this says.
Also, I don't know if you, sorry, I don't know if you, talked about this, but, specifically the rules specify about like how you can stack segments versus like.
Yes,
make-
so that is in,
Of course.
Oh, wait,
uh,
what?
don't worry about it.
Yes, you gotta read it.
Yes.
What did you cover last week?
Don't worry about it. There, I think it's somewhere in this slide. Yeah, basically, it's one of the slides in here. It talks about the idea that yes, you're right. You can stack segments in a variety of different ways. Oh wait, I think it. I don't know where it's in one of the slides. But yeah, basically, one of the slides does cover this topic of like why don't we stack cells vertically? And the answer is you totally are allowed to stack segments vertically, but there are just special rules about it. So
Separate path to the ground. Key to the vertical one.
Yeah.
Mechanical and electrical, I think.
the high level idea is that if I put one segment and then I put another segment on top of it, they want to make sure that like the force isn't going into the other segment. You're proving it's going through the box into the frame directly. And so there's just a little bit more effort that goes into it. We looked and we were like, well, we didn't really see a significant advantage to stack anything. Based on compared to other designs.
I think we basically said, why stack things to deal with that complication when we can just make each individual thing skinnier and taller?
And that's why you have that. So yeah, there you go.
We do it, you like wire the segments parallel or like.
All of them are in series. Yeah, and so yeah.
All of them are in series, but we can do whatever.
Yeah, so there's no rules. Like you could do them in series or parallel or whatever. But yeah, we particularly, because of the fact that we have a 140 series for parallel cell configuration, for us, it is most optimal to have like, they don't explicitly ban it, but they very strongly recommend that you do not try to run segments that have cells in parallel, but in separate segments. Like, how we will have like 4 cells in parallel. They recommend trying to put the 4 parallel in the same segment together rather than splitting like 2 and 2 and then having more. Because the idea is that when you split it up like that, you just get higher voltages between your segments, but now you need to track twice as many independent cell voltages because these ones could fluctuate differently than these ones, and they're like, fuck you, keep them all together. You don't have to, but they're strongly recommended.
Also, a more serious issue, I think, about putting like multiple segments parallel, if they're not exactly the same amount of charge when you connect them to each other, then you get extremely high currents as they instantly equalize the charge level, and it keeps up them if they're far enough, then that can be really dangerous. And then in use, they're not going to discharge exactly the same, as you have some balancing issues, and it can be dealt with. But if you put them in series, then you just don't have to worry about that.
Yeah, so that's just the general practice is that your segments will be connected in series. I am unaware of any teams recently that run parallel configurations. Every team I've seen just puts their cells in parallel in the segment and then run series. But in theory, you could do a parallel configuration.
In theory, you could make an e-box for every individual cell.
Yeah.
Have 560 segments. Then when you plug the bigger size.
Oh yes, I've seen that. Mm-hmm.
Oh yeah, we did talk about this. The simulator container, the entire frame would just fill with cells.
You would just have to do firewalls technically between the frame and the driver, but you can do that.
Well, but the frame can be a firewall, can't it?
You're right. It is UL94V0 rated. Anyway, so jumping all the way back. Yeah, so jumping back and quickly finishing up our bus bars before we wrap up for today is like I mentioned, you want to basically make your bus bars as big as possible. If you can come to a design that demonstrates that the bus bar at a given size is large enough that it will never overheat and doesn't have to worry about thermal problems, then that's great. But ideally, if you have no good way of modeling that, then you can just make it really big, cover the whole surface, and then they make and it's bonding and flexibility quite easy. And it means that then you don't have to worry about overheating. You don't have to worry about cooling the bus bars ideally. Hess strongly recommends that you keep your bus bars to 1 to 2 millimeters thick. We exceed that significantly with the guy on the bottom, and it makes sense. They say that they can bond higher ones, but they strongly recommend they're like, yeah, it's way more efficient, it's way more standard to make a thin 1 to 2 millimeter bus bar that spreads out rather than having one thicky boy, and that then lends really well into the larger design guideline of try not to send your current down and then through a tiny strip and then back up. Instead, try to have it evenly go throughout the pack.
Does could potentially be more difficult.
So that's the thing. But yeah, so there's all those considerations. Yeah, and obviously, all these slides are always available in case you want to just like go back and check them. And then finally, like I said, the BMS sensing connections. Like I talked about, there's the option you could like get a PCB where you could actually bolt that PCB to the cell holder, and then you could always bond directly from the bus bars to the PCBs. And so that's one thing is that we originally had done our whole weird plan of, the spot welding a piece of nickel and then soldering to that and that whole plan. Just, making one cohesive design from the beginning and then like coordinating your bus bars with that. So you can say, put the bus bar right next to the PCB and you have the space available for it would be way better. Because right now we'll have like bonds on the end and it has had to bond from like the middle all the way over. You'd have issues. So, yeah.
Maybe, I'm a little bit confused about like something large and like I don't know.
So the BMS needs to somehow have wires connecting it to the voltage sensors and the battery. And you can either use like a bunch of little wires that you have to connect somehow, or you can make a circuit board. And the circuit board is a bunch of little wires on a sheet of fiber. And so it's just an easier
You
deal.
still need to attach that circuit.
Right, but the circuit board have like pads where you want to attach it and then where to box it.
Yeah.
And it lets us solder the fuses on instead of having to like then figure out some way of mounting the fuse to a piece of floppy nickel, and it's like this is just easier.
Yeah. All right. So yeah, obviously as demonstrated, we've gotten through 15 slides. So it sounds like we'll be continuing this next time. Obviously, as I mentioned, there is a recording available online of all of this stuff, and the slides are all available if you want to go through them. I think they're quite verbose. Yeah, well, it sounds like we'll pick back up next time with the BMS board. Cool. Thanks, everyone. Of course.
Should I be involved in the presentation about BMS board?